Okay, Alex should know how terrible of a substitute I am. Okay, so I'm going to be talking to y'all about Turing machines. We were originally supposed to cover 3.11 and 3.12 of Nielsen and Schwang, but ironically, despite the fact that I'm much more familiar with circuits than I am with Turing machines, I felt more qualified to talk about Turing machines and decided to leave the circuits for our resident computer scientist. So first off, why do we care about Turing machines? So naturally, quantum computing is going to necessitate that we understand some idea of how to compute in general. Otherwise, we're just doing quantum physics, right? So computer scientists have done a lot of work on contextualizing what it means to be a computer and be able to do a computation and all of these things. And moreover, they've like formalized what it means to be an algorithm when two algorithms are equivalent. And there's this whole body of work that it would really be a pity if we couldn't use it, right? If it's already established, rather than working from scratch, it's easier to just grab what computer scientists have already done classically and sort of adapt it, just throw the word quantum in front and use that. And Turing machines are really at the heart of how classical computer scientists think about computers, is my understanding. Okay, so specifically understanding Turing machines are good for complexity classes. What are complexity classes? One, they're the bane of my life. Two, they're the way you classify how difficult it is to do an argument. So sometimes you'll say something's efficient or it's not efficient, or you'll hear people talk about, you know, how much time or how many steps, or reducing to something in polynomial time. All of that has to do with complexity classes, which I don't think we use too much at this point, but suffice to say, it's a measure of how hard something is. And when you get down to it, they're all tied to Turing machines. So if Turing machines can do it easily, it's easy, and that's normally considered in P, or polynomial time. And if Turing machines can't do it quickly, it's in P, or non-deterministic polynomial time. There's way more than those two classes, but those are like the two you hear about. And then finally, and this was left over from when I was supposed to talk about circuits as well, you also want to talk about circuits so you can draw out these algorithms pictographically and simplify your calculations, so you don't just have to write out math all the time. Okay, so on to the section in question. So they start off by going over algorithms, which are just a list of instructions to solve a problem. And we think of algorithms in terms of computer algorithms, which were originated by this lovely lady at the bottom right. That's Ada Lovelace, the first computer programmer, full stop. Some people call her the first female computer programmer, but that implicitly implies that there was another one before her, and there wasn't. But so computer programs are a list of instructions to solve a problem, but you don't necessarily have to be a computer to run an algorithm. Any set of instructions for how to solve a math problem, any sort of computation, that's considered an algorithm, which is why the words algorithm and algebra actually have the same origin from this one dude whose name I will never be able to pronounce, who is the father of algebra. So there's your fun fact of the day from me. Algebra and algorithm are both named after the same dude.
Can I ask a question?
Go for it.
Where does that name come from? Like what?
Persian.
It's Persian.
Yes.
Okay.
So he was a polymath, like I think 9th century astronomer, mathematician.
Well, we know a Persian, so we'll have to ask her how to pronounce it.
Yeah, so we might record her actually pronouncing this name, but the words algorithm and algebra come from the Latinization of this name. Okay, so yes, all right, so there's your fun fact of the day. So you have algorithms which describe how you do computations, and David Hilbert, who quantum physicists would be more familiar with through like Hilbert spaces, he asked the question, is there an algorithm that can solve every problem in mathematics? This was kind of his big gauntlet throw to the whole field of algorithms, because it was established before computers. Ada Lovelace also lived, over a century before Turing, I believe. So, she was writing computer algorithms before computers were really formalized. So he's then taking that field of algorithms to say, all right, can we just write all math problems this way? And can we just write a general enough algorithm that can solve every problem? And he thought the answer to that was yes. But Church and Turing, whose name I've misspelled, who are absolute mad labs, are like, absolutely not. You can prove that that's not true. But moreover, we can tell you how to solve every problem that you could have written as an algorithm. So you can't write every math problem as an algorithm, but the ones you can, Church and Turing say that they can give you a description for how to solve it. And spoiler alert, that's going to be the Turing machine. So what are Turing machines? Well, historically, people didn't refer to computers as computers. Computers were actually women who would sit down and write out their math calculations. And if you've seen Hidden Figures, that's why they're called computers. Computers were just called machines. And there are three main types of computers that have existed. There are analog computers, which run off of like mechanics, like steam. There are classical computers that run off of electricity. And then, now we have quantum computers, which are almost always interfaced with lasers and optics and really modern physics. And amongst these three types of computers, these two are Turing machines. So for everyone in this group, except for myself, Surya, and Roy, and Eliza, if she decides to return, I suppose, every computer you've ever touched is a Turing machine. Every computer you've ever programmed is a Turing machine. Even, though the picture I have on the far left is the difference engine, it's like the first attempt at a computer. All it does is add and subtract numbers. That's a Turing machine. So when it's described in the book, it's described a lot more abstractly from that, but just think Turing machine, a normal computer. So it always has four parts at its most basic set. You have your program, which is just your set of instructions. You have a finite state control, which is like a processor. So basically, you can kind of think of it as like a running calculation. So before you're done doing all the steps of your program, you have to have some way to keep up with where you are in the program. That's your finite state control. Then you have a memory, which is your tape. In the Turing machine like scenario, when they're talking about how you set up this intuitively, it's literally a piece of tape, or you can in each box like write one symbol. And then you also have a reading and writing tape head, which just goes along your tape, and you can read off a symbol or you can write a symbol. Okay, so that's how all Turing machines work at their most fundamental level. But a simple example, lest again we take too far away from the heart of what Turing was trying to describe, is pen and paper. So Turing put forth his model of a Turing machine not just to describe like these big machines that are like mysterious and can do all calculations, but also to describe what it means for something to be calculable. So this includes what people can do. If you can like sit down and write out a calculation, and to try to elucidate that connection, which comes back to like the beginning of Turing machines, I thought I would just point out that like a pen and paper can also be considered a type of very crude Turing machine. So, your programs may be given by the algebra of your problem. You're trying to solve y equals mx plus b, and your state control is your local mathematician. They're keeping up within their head. The tape is the paper that you're writing on, and the pencil is like going through writing out each symbol. And then when you've done solving the problem, your output state is whatever the last line of your homework is. So Turing machines are described in this setup, and it's a bit abstract, but at the heart of them, they're just meant to describe what it takes to calculate something. Even if it's on pen and paper, you can kind of appropriate that. So at this point, I could pivot, and I could now go into what the book describes as like how exactly these programs are described to go through, but the rest of the book doesn't really do that very much. We don't focus on like, here is a Turing program, and let's go through and make this Turing machine analyze something, because what we're doing is quantum computing, which is slightly different. So although I have those slides, I thought it might be wiser to hold off until the resident computer scientist could describe those to us. And instead, I'm just going to pivot and now talk to you about the Church-Turing thesis. So the Church-Turing thesis is a statement put forth independently by Church and Turing to say that the class of functions that are computable by a Turing machine corresponds exactly to the class of functions which we would naturally regard as being computable by an algorithm. Keep in mind, algorithm not necessarily associated to like a mechanical computer. An algorithm could be like what a person could calculate. So it basically says if you can solve it, you can solve it on a Turing machine. And this is probably true. It's kind of a hard thing to disprove, but there was work done beforehand to try to describe all sets of algorithms. And so there were two other mathematicians, one who described functions as recursive and another using something called like lambda computable. And all you need to know about that is they showed that for those two classes of computable functions, it completely corresponded with the class of functions computable in the Turing machine. So you had these like abstract mathematicians working on what it meant for a function to be calculable, and it turned out to be exactly the same thing as being able to put it on a computer and run it. So we have good reason to believe this is true, but it's kind of hard to prove definitively. So we just kind of take it for true. This is also thought to be true for algorithms computed by quantum computers. So if you can do something on a quantum computer, you can also do it on a Turing machine. So any program you can put on a quantum computer, you could theoretically run on your laptop. So what is the difference? Why care about Turing machines and quantum computers if we already have laptops that can run everything? Well, oh, okay. Yeah, so that takes us to the next thing. There are some things that you can't calculate on a Turing machine. So I decided to do some audience participation in honor of Roy. So before I answer the question of why do we care about quantum computers versus Turing computers, we're going to first point out that there are some things that are not calculable. And so this is a problem from the book. And if anyone would like to chime in or scribble on the laptop screen or what have you.
Well, I don't think I should go because I know this one.
You can go, Sylvia.
All you, Lydia, go for it, man.
So this is basically, it's called the halting problem. And this is, I think, one of the first examples of saying of an algorithm of a problem that doesn't have an algorithm to solve. And I think the way they go about it is most of these problems they solve by contradictions, where you assume that there is a Turing machine M that can solve this algorithm and output whether it is a general Turing machine that takes in a problem and outputs out whether it halts or not. And you can use that and you can create a bigger Turing machine with this as an input and two copies of this and say if it halts, the bigger machine doesn't halt, and if the smaller machine doesn't halt, the bigger machine halts.
Yes.
So if your smaller machine is an algorithm that tells you if it's going to halt or not, your bigger machine, you can never know if it's going to halt or not. So essentially you reach a contradiction.
Mm-hmm.
Yeah, nice. I like that.
Yeah, so you take a blank tape and you feed it into a bigger Turing machine that says whether or not this one halts.
Yeah.
Yeah. Right. And then you'll find that whenever this one halts, this one never halts, and this one, whenever this one doesn't halt, this one halts, correct?
Yeah.
Yeah, so they contradict each other. They go on, and you always end up in an infinite loop of like this statement is false or something like that.
Mm.
So good job, Surya. Very good explanation.
I have a question about the previous slide. So when we say something is computable by an algorithm, do we assume that we have infinite time resource, or do we assume that it is computable in finite time?
You assume infinite memory resource. So
infinite memory.
So you assume infinite resources here. Yeah. So that's the difference between this and the next thing I'm going to talk about is here there is no assumption on resources. So given infinite time and infinite memory, you can compute it. You know, it might take you a long time, but you can do it.
Okay.
Yeah. So that's the key difference, right? So first off, we're going to point out there are some problems that don't have algorithms. We don't assume you can put those in a Turing machine, but there are other problems which have a different limitation to them. So that was a bit word salad. Anyway, we're going to focus on the extended Church-Turing thesis. So the difference between this and the Church-Turing thesis is in this word efficiently. So this says a probabilistic Turing machine can efficiently simulate any realistic model of computation, where the word probabilistic is sometimes included, but it's not necessary. You can show a probabilistic Turing machine is equivalent to a non-probabilistic Turing machine. So the word efficiently here is a problem because it hits at the heart of Zach's question. It's like, do you assume infinite time? Do you assume infinite memory? Well, if you're saying efficiently, you can't have infinite time and memory. And oftentimes in computer science spaces, the word efficiently means polynomial in time or polynomial in space, you know, so a reasonable calculation, if you will. But that kind of throws a monkey wrench into the whole situation. What is a reasonable calculation? What are reasonable time scales, and what is a realistic model of computation? Like, what does that mean? The language in the extended Church-Turing thesis is a lot more vague. And whether or not this is true is a lot more up for debate than the Church-Turing thesis, which, you know, had a very strong fundamental in mathematics. This is just sort of an extension that came about later through computer scientists. And computer scientists, a lot of them are very convinced that this is true because they're basing it on the strength of the original assumptions of the Church-Turing thesis and the strength of the computational models for algorithms. And when I mentioned complexity classes of like P versus NP, when I like P is easy and NP is hard, they believe that is true, that they don't collapse in on each other. Because if the extended Church-Turing thesis is true, then there's a distinct difference between how difficult an algorithm is. Like, deterministically, you can describe this and you can list out what is an efficiently calculable algorithm and what isn't. So speaking more on efficiently and going off of the extended Church-Turing thesis, she said, okay, well, here they say a Turing machine can efficiently simulate any realistic model of computation. Are there any other models of computation? How do I know when I have a Turing machine before I can, expand upon that? So we're going to use that word efficiently again, which means like in polynomial steps. We're going to say if we can map from whatever we're using to do our calculation to a Turing machine described by that like tape and writer and tape head setup in polynomial steps, then they're both the Turing machine. So the difference engine is it's just gears that add things and subtract things, and you can figure out how to do that immediately on a Turing machine, right? You can just have your memory go through, and if you have like binary bits, your tape head can like change your internal state by 1 for each time that you have 1, and by 0 each time you have 0, and just continue through your tape, and you can add this way. But you can't map a quantum computer to a Turing machine. So why not? This is another audience question. There's a very clear reason that you can't efficiently go from a quantum computer to a Turing machine. An almost intuitive reason.
Is it because the Hilbert space blows up exponentially with qubits?
Yeah, it's because the Hilbert space blows up exponentially with qubits. So yeah, so for every 1 qubit, your Hilbert space goes as like a power of 2. So you have n qubits and you have 2 to the n in your Hilbert space. And so a fully quantum situation in physics is going to naturally be described exponentially on a Turing machine. So you can do it on a Turing machine, but you're gonna naturally think that there are gonna be some problems that a Turing machine is not gonna be able to describe in polynomial steps. So that's the first difference between a Turing machine and a quantum machine. It's that a quantum computer is not a Turing machine. That's a little bit impressive since most things are. And then you can also describe a Turing machine through this idea of universality, which is so kind of jumping around here, but so I said you can map anything that is efficiently mapped to a Turing machine is a Turing machine, but there's also this idea of a universal Turing machine, which is often described as a Turing complete machine, which will basically any calculation you could do on any Turing machine, you can do on this Turing machine, which is a very abstract computer science description, but you can basically think of it as a PC. A PC is a universal Turing machine. So it can simulate all other Turing machines because you can run different algorithms on it essentially. And a Turing machine is by definition like one algorithm in its inception. So they can solve all of the other problems that Turing machines can, and so you can very much like just take a Turing machine. Every type of Turing machine is one huge entity. So just because, so when I say that like quantum computers can't be mapped to Turing machines, but Turing machines can all be mapped to one another, it really is saying something that quantum computers might have this inherent difference where you can be Turing complete and you can do all these normal algorithms efficiently. But there might be quantum algorithms where a quantum universal machine could solve all of them, and it can maybe do them faster than a Turing complete machine. Okay, and so that's the real difference, is that, you know, we have every computer that we've ever touched up until like, I don't know when the first quantum computers came out, but like the 2010s, every computer, every pen and paper is a Turing machine. And now we have this new type of machine that can do all these quantum problems and can do them faster, but are not Turing machines. And so there's this clear divide in computing. But this is all like theoretical. So when does it actually matter that you have a Turing machine or you don't? Well, let's talk everyone's favorite example of factoring. So factoring is not efficient on classical computers. This is a very important assumption. So it's considered to be in NP, which is the complexity class of problems that are not polynomial in time on a Turing machine. And the reason this is a very important assumption beyond just like complexity theory is because RSA encryption is based on it. So like your banks and your internet protocols, all of them assume that it's hard to factor really big numbers into their prime factors. And so they use prime factors of big numbers to secure everything. And so computer scientists really, really want factoring to be inefficient on classical computers. And there's good evidence to show that that's true. But then this guy here on the right, which this is like a pencil drawing of an actual like portrait of him, which I just thought was cute. This is Shor, and he took a number theory class one day and it gave him an idea of a quantum algorithm that could actually solve this factoring problem efficiently on quantum computers. And I'm pretty sure we're going to cover Shor's algorithm at some point because it's the baby algorithm of like every quantum computing lecture in class. But suffice to say, he showed that it's efficient. You can do it in polynomial time on a quantum computer. And we've already established that quantum computers are different from Turing machines. Okay, so we have a realistic model of computing that does something efficiently that a Turing machine cannot, which really takes a hammer to this extended Church-Turing thesis, right? Because it said if it's efficient on a Turing machine. But we've already kind of established that quantum computers are not Turing machines. So this sort of evolution of this one algorithm really put a damper on people. in the relations rather between your computer scientist and your quantum physicist, because now one of these three things must be wrong. Either the extended Church-Turing thesis is wrong. Computer scientists really don't like that. But it assumes that Turing machines are not the only valid computers. And from a physicist perspective, that's honestly pretty believable. So if the extended Church-Turing thesis is wrong, then there's a benefit to using quantum computers, which are not Turing machines. If it's correct, there is no benefit to using quantum computers. Another option is that Shor's algorithm is wrong. Well, Shor's algorithm is based on number theory and quantum mechanics. So if it's wrong, quantum mechanics is wrong. And I find this incredibly doubtful. And most physicists find that incredibly doubtful. The third option is that factoring is hard, is wrong. And it turns out that factoring is actually not as difficult of a problem as we thought. And there's also an efficient algorithm on Turing machines. And computer scientists don't want that to be wrong either, but they're much less protective of it compared to the extended Church-Turing thesis. However, there is some implications that if factoring is efficient, then our two main complexity classes that everyone talks about, P and NP, so polynomial time and non-deterministic polynomial time, those are the same. If those are the same, all of complexity theory collapses. So TLDR in this whole rundown is that one of these things must be wrong because our buddy Shor has an efficient algorithm on a quantum computer that is thought to be not efficient on classical computers. So one of these things is wrong and something must break, something big. So this is like the big motivational understanding of Turing machines and also like quantum computers that I wanted to get to. So this is the thing that I feel is the most important, is that the existence of quantum computers and algorithms like Shor's algorithms imply that we're at the cusp of something interesting. So all the rest of the slides that I have are descriptions of how a Turing machine works. But as I said, I don't really feel confident going through those. So I'll just like stop right here, if that's all right with you, and anticlimactically end this. So yeah.
Yay. Okay. So first of all, I'm not a computer scientist, so I'm completely comfortable saying this. Let's throw away the extended Turing thesis.
Yeah, I mean, I don't know if you can tell my bias from my little asides that I've added, but I don't think the extended Church-Turing thesis is true.
It just seems so unmotivated to me. I don't know.
Yeah, so the Church-Turing thesis, I think, is incredibly motivated. It lines a lot with, it doesn't look at algorithms as being a facet of computers as we think of them today. It looks at algorithms as a mathematical object. That I thought made a lot of sense. But the extended Church-Turing thesis is very wibbly wobbly and it's like efficient, reasonable on a real computer. Maybe he doesn't think quantum computers are real computers, but that seems like kind of arbitrary to me. So, but you know, computer scientists think that they have proven the extended Church-Turing thesis. I've seen like proofs of it, but you only need one counterexample. And we have a counterexample, so I don't know.
Yeah, I'm more likely to just chuck out ECT because when it was proposed, it was they had no idea that there could be something that could actually harness the extended Hilbert space. I mean, the Hilbert space, right? You don't have access to that exponential space to work on. So it's way more likely that quantum mechanics is right and this assumption is wrong. I also don't want P equal to NP to be wrong because we can all pack our bags and go home.
Right. Yeah, everything is officially computable on
Done.
everything. I feel like P equals NP is extremely unlikely. A lot of computational theory is based on the fact that they aren't equal.
Yeah.
Because like I feel like all of computer science collapses if P is equal to NP.
Yeah. Because if you can find one example of an NP complete problem that you can do that you can run in polynomial time, you can map every single problem to that and then map that to polynomial time. So it's just disastrous. We just don't want that to happen.
Yeah.
I
So
have a I
yeah.
have a really important point. In the Millennium Prize problems, where this is listed, does it say you have to prove that it's true or false? Like, what if it's not what they expect? Do you still get the $1 million?
Hmm.
I forget who posted these.
P versus NP problem. Okay, let's figure it out.
I think you just need to prove one or the other, like either they're equal or they're not definitively.
Oh man. The website where you Google it, it says
Mhm.
it describes the problem, and at the end it says this problem is unsolved.
Yeah, I don't think it's ever going to be solved. That's a little bit frustrating from my understanding of computer science. It's a little bit frustrating that technically speaking, you can't like solve any of the complexity theory problems. Like prove NP is not NP, or prove that it's in NP but not NP, and like you can't solve them. We really hope that they're not the same, but you can't solve them, and that's a little bit frustrating for me.
I think I know a huge class of people who would want them to be the same,
Yeah, I mean,
and
I feel
I
like
really
either
don't want them
way.
to be the same because that's what's interesting. Like figuring out what's in P and what's in NP. If everything is in P, I guess it's good in a way that everything is efficient, so we should be happy about it. But well,
You want that job security.
Yeah.
yeah.
Oh, I'm gonna take a different stance. I hope P is equal to NP only on quantum computers. I hope we figure out an NP complete algorithm on
Ooh.
quantum computers, and then it really pulls that divide between the Turing machine and the
Ooh, that'll be interesting.
yeah, right? Because
Yeah.
we've established they're not the same machine. So what does this mean for complexity theory? Who knows,
So if you're trying to say if we can prove that NP is equal to BQP or something like that, and
Yeah.
then everyone will start becoming quantum programmers. Everyone just abandon classical programming. That'd be excellent.
So yeah,
Love
so
it.
I was kind of scatterbrained because I made this today. I found out I would need to sub in today. So Dominic and Cameron, y'all don't already play with quantum computing. What do you think about this short rundown?
I mean, to me, it makes sense that there's stuff that should be possible on a quantum computer that is not possible on classical computers, just because of like superposition and entanglement stuff.
Yeah, so a fun result, because people are not exactly sure what makes quantum computers stronger. Like obviously the Hilbert space is bigger, but computation wise, entanglement alone is not enough.
Yeah,
And I think superposition alone is not enough. It's really weird. People are not completely sure. I think relative phase, strangely enough, is really the sticking point that like classical computers have a hard time with. Which is not what you would expect. You would expect it to be the entanglement, but it's
No,
you can
I did
simulate.
expect it to be entanglement.
Yeah, so you can simulate.
superpositions.
So you can break down all your quantum computing gates into what's called a Clifford algebra, which may or may not be an algebra, and you can simulate all of them on any algorithm that uses those on a Turing machine, easy, efficiently. But if you throw in a relative phase, so you have like 0 plus e to the I phi 1, now it's inefficient. Like that's not at all where I thought the stumbling block would be. Spooky action at a distance, come on. And they're like, nah, relative phase, man.
I think superposition. I think I read this paper a long time ago, just talking about just superposition. Like if you had a model where you had just superposition, you could do that efficiently on a classical computer, on a probabilistic classical computer, which you now know can be mapped to a deterministic Turing machine by using more memory. So it was like Marguerite said, it's so weird that okay, it's not superposition, which seems likely. It's not entanglement, which seems even more likely. What the heck is going on?
Yeah, I don't know. It's some funky quantum physics is going on.
Wow, I did learn something new today.
Yeah, me too, because like I've got a quantum background, but no quantum computing or computer science. So just from a physics background, purely I thought it was superposition was like the big advantage of quantum computing. You could have like qubits be in more than one state at once.
Yeah, I mean, when I first heard about quantum computing, I always heard the pop science like, oh, it's because it's like inherently parallel, right? But that's not true. That's not where the advantage comes from. I mean, and that kind of makes sense because if it was where the advantage comes from, I could map it in polynomial time because I just
That's the
linked
problem.
together
Yeah.
my quantum computers. I just have one more Turing machine. So
What's I think the way I usually think about it is have you guys gone over teleportation yet?
Yes.
yeah, Eliza did teleportation.
Okay. So in teleportation, you know that if you have just entanglement, you can't simulate it. Or if you had just a qubit channel, you can't simulate it. So individually, both those resources are useless, how much ever of it you have. But you put them together, then you can do this qubit moving thing, right? You can
Yeah.
transport a qubit. I feel like it's not straightforward to think about. It's like orthogonal resources. You can't have just one and as much of one and you can do it. You need a little bit of the other also. That's usually how I think about it.
That's an interesting thought. I never thought about it that way.
How much is known about like the resource theory for quantum computing?
Oh, I don't know.
I don't.
No
I feel
idea.
like that's a question for Mark.
Yeah.
Guest speaker.
Oh, he would love to be a guest speaker. We would be sitting here for 2 hours reading a textbook. I'm
maybe while he's stuck at home, with the baby.
yeah. he can read quantum computing for babies to us, and we'll gain something from that. But yeah, I just hope this was. I felt very scatterbrained going over it because I don't know a lot about this. A lot of what I know is like trivia. So like I know what makes the Turing machine. I know who invented algorithms. But I know that the word algorithm and algebra come from the same word. So I hope that this was, it's somewhat informative to give the general landscape.
Yeah, it was for sure.
Yes. I have another question. Why is it that all quantum algorithms seem to fundamentally be just like one of two algorithms, just like phase estimation or the search algorithm? Why does it all seem to just come down to that?
I think I have an answer to that. It's kind of a heuristic answer, but it's the only ones we know so far that seems to
Okay.
have an advantage. So we try to map everything to that.
I think my question is more so why are those the only two we know after decades of research?
I mean, so I think, going through it too, it's like, so as I was saying, like you can map between algorithms in polynomial time and their equivalent. And so even if you do come up with one that's not one of those two, if you can map it to one of those two in polynomial time and people already know those, just do that. I already know how to do phase estimation. Let me just do phase estimation.
Okay. Yeah.
Alright, didn't we recently get an email from Mark saying somebody's going to present on a paper which is the quantum algorithm has an actual advantage of the classical algorithm and it's not phase estimation or Grover's?
I have not, no.
I don't know. Let me see if I can
Should
I
we stop
wanna-
recording, by the way?
Yeah, yeah.
Okay.